A little bit delicate to measure, but we got delicate when we started to measure atoms. And this isn't even in atoms. This is easy to find experimentally, even in soap bubbles, so, and on the street in oil films. So it's relatively easy to discover this phenomenon. This phenomenon is really not puzzling if the light were waves, but you remember that we discovered that it behaves like particles. So what this is, I say 16%. What is it 16? What is the 16%? It's the probability. What we're plotting here is the chance or probability of reflection. Now let's see how frighteningly confusing that is. Because let's say, suppose that I took a thickness, a very thick, I got the 4% corresponds to the front surface. Suppose I bent the back surface, or I didn't have it, and I got 4%. Now I put this other surface here at just the right thickness so the reflection is 0. I'd like you now to explain to me how with particles that could possibly occur. Because if the thing comes down and gets, you see, if it either does or doesn't get reflected from the surface, you would say. Well, is you going to say it's reflected or not from that surface? Make up your mind. If this surface is far away, it gets reflected 4%. So let's suppose it is reflected from this.
How could you have a piece of glass that has only one surface?
Well, the other surface is irregular and far away. What you're trying to do is, if you tilt it at an angle so that the light from it doesn't come to you. Okay.
Photon detector in the glass.
It's off the first
That
surface.
won't quite work, huh?
It's off the first surface.
It's what? Well, I'd say if you put this surface down here at an angle so that the reflection from this surface goes somewhere else, then it's 4%.
Yeah.
If it happens to be exactly that way, it'll add up to 8% because that sends it back too. That's what I should be careful with. But at any rate, the problem is that we would like to say the 8% is 4% from here and 4% from there, and that would be all right, but how are we going to get 0? You say, oh, well, let's make up our mind. What happens at the first surface? Does the light get reflected or doesn't it get reflected? Make up your mind. If it gets reflected, how do you undo it? By putting another surface here. In other words, if that photon is rushing forward, the 4% of 1 out of 25, how is it possible by putting another surface here, turn it to 0, to stop it, huh?
An absorptive color.
But you're doing it under here. It's already made up its mind to start back. Then you have to rush back and catch up to it and eat it up or something. So you have to haul it back. Where do you have to do something to it too? It's not just getting rid of it, because you find it down here. I forgot to tell you, that's important. Good, it's not absorbed. Because if you put the other photomultiplier here and the one up here, this one is always getting the ones that don't go here. In other words, when this, if you'd ask how many come here and made a plot of that, you'd have 100% of them with that thickness. And then at this thickness, it would be down to 84. And then it would go up to 100 and down to 84. What I'm trying to say is, very simple idea, though it looks mathematical, is the total, that every photon either ends up here or here. Nobody has ever lost, okay? So if you start out by supposing that the front surface reflects the particle, then you can't figure out how you can get the back surface to catch up with it and make it not do it so that you can get a 0 here, or at the next point, and so on. And that's the most cogent argument. It says it can't be little spots, because if it were little spots that would get reflected, then you can't catch it back. As a matter of fact, it's virtually impossible to explain this from the point of view of particles. And Newton went a little bit crazy. I don't mean he was insane. I mean, he had very complicated theory for this. He said the following: since the reflection strength depends upon where the back surface is, as you see, it must be reflected from the back surface. But since the amount of reflection depends upon where the front surface is, the degree to which the back surface reflects must depend on where the front surface was. So he proposed the following idea, that as the light comes down, it excites some kind of a disturbance in the glass, so that the back surface, when the disturbance gets to it, it changes the quality of the back surface, so that the back surface will reflect 16% if the disturbance has gotten here just right, or 0, depending on how that disturbance arrived. So he had the theory, it's reflected by the back surface. But the amount of reflection depends upon a condition at the back surface which is affected by some sort of a wave that comes from the front surface to the back surface. Not the light wave, because he didn't have light waves, but a wave of disturbance that the front surface sends to tell it that the photon has just come by here in order to change that number. Rather complicated. He called it fits of reflection and transmission. As you see, what's not reflected is transmitted through. Fits in his language meant chance, as far as I can interpret it. But he didn't, that isn't right either, that it's reflected by the back surface, and if Newton were here, I could have convinced him immediately. But he didn't think of this argument. He didn't think, all his experiments were with two surfaces. If you add a third surface, right, then it changes all the things again. With three surfaces, even when a place that would have been zero becomes something. And places that are something are changed. And you can get zero at some other thicknesses and so on. In other words, the reflection is affected again by a third surface. If it was being reflected at the back surface, how could it ever get to the bottom surface to find out and to be caught and so forth? So we have the same problem between 1 and 2 as we would have between 2 and 3. We can't decide when it's reflected. It can only be reflected on the last surface. How does it ever know which is the last surface? Maybe it's got another one coming up soon. So the whole thing was very difficult. And there has never been a satisfactory model of the very simple process of reflection of light from thin surfaces. Or, in fact, after that, for any other phenomenon. Satisfactory in the old-fashioned classical view. A logical hocus pocus has to be done quantum mechanically in order to describe these things, and that our talk with the boxes was an example of the kind of difficulty. This is another example of the type of difficulty when you try to reason in a straightforward way, in a classical way, about a simple phenomenon.
When there's a third surface, you said it sometimes goes to zero again, but not those same points.
Yes, it just changes that curve to a different one. As a matter of fact, he made one with 32 surfaces, which would also do this. You see, we can't change his thicknesses with his piece of equipment. I've imagined an experimental thing where I can either change the surface or replace one by another, the different thicknesses, okay? We're changing thicknesses. He doesn't change thicknesses. Now, I have 3 surfaces. I got a lot of changes I can make. So I have to plot it in a more complicated way because I have to tell you which thickness I mean that I'm changing and so on. But for every combination of thicknesses, there's a degree of reflection, which can sometimes be zero if the surface is placed just right for the monochromatic light, and at other times can get up to, with 3 surfaces, 36%. I haven't made a mistake. 12%, 36%. Yeah, right. Yes. A little correction. By this time, the percentage is so high, I have to make a correction for the 96% of 4 business that I was doing before, but it's roughly 36%. So it varies in a similar manner with the 2 different thicknesses. But let's just talk about the 2 surfaces. The 3 surfaces was only to indicate that the ordinary arguments don't work. It depends on all the surfaces, if we had several different materials and different layers. And it cannot be described easily by an ordinary particle picture, and we've gone crazy. I mean, not crazy. I mean, we've had to back up. All we have is a method of figuring out what will happen, which has no mechanism in it. And so what I want to now tell you is what the rules of what we actually do to calculate the probabilities in situations like this. And you'll be horrified. I mean, you're well prepared to be. It's completely without model, all right?
Before you erase all that, what happens if you aluminize the far surface and half silver the upper surface?
It just makes all these numbers stronger. I've only had 4%. A half silver to be something like 50%. And when you have different numbers here, you get curves are stronger. They go higher or come down. And I have to think a minute whether I can get to 0 or I can't get to 0 if this is solidly aluminized. No, because nothing can get through. And it's also all be reflected somehow. But if they were both half silver, you get a curve just like this, but much stronger ups and downs. This only rises to 16%. By the way, if you use water instead of glass, then the numbers aren't 4%, they're somewhat slightly different. glass, water doesn't reflect quite as well as glass, and I think it's closer to 3 or 2%. I think maybe 2% or something like that, I forget. Okay, same idea though, all right? So now I'm going to tell you how we figure these things out. Because although from the point of view, this is what's most curious, from the point of view of how it works, this looks, it's very complicated. You can't get a nice model. It's very difficult. It breaks the head. But the formulas, the rules for computing the probabilities are delightfully simple. The numbers that come out and on the different situations are easy to figure out, as long as you're willing to take arbitrary, crazy rules without knowing what it is. I can give you an example of the situation of a way, but it's not a perfect example, it's just somewhat of an example. The Mayan Indians had a pretty good knowledge of astronomy. They could predict when Venus would appear as a morning star and when it is an evening star, or where they could predict when eclipses would occur and so on. Let's take the example of Venus. There, in order to do Venus's, to figure out when Venus would appear and not appear, they knew what corresponded to a period. It took 584 days to repeat the cycle. That if Venus appeared as a morning star, just appeared on the horizon, then 584 days it would appear in the same place approximately. Okay? So all they had to do was count up the 584-day periods to see when it would come back to where it was before. And this could have been done by making a bowl, putting bowls and counting out every day, taking out one bean and counting the beans. Actually, however, they had developed a much more elaborate method of doing the counting and figuring, which was arithmetic with a number system and algebra, arithmetic. Arithmetic with numbers, and just like we do. We don't count bowls to add numbers. We can add numbers and subtract numbers and figure out what's going to happen without actually taking, if I wanted to subtract 27 from 62, there's two ways of doing it. I put 62 things in a bowl and I take away 27 and I count how many are left. So if I know how to count, I can do additions and subtractions. But if I wanted to subtract 276 from 382, it's too much work. So we have developed techniques for doing that, which in our civilization every kid in school learns. In their civilization, no doubt, every kid did not learn. But damn this thing. But they had, because I step on this, well, all right. But they had a arithmetic system that the priests knew, okay? And they would be able to predict this because they could count their days and make the subtractions and figure out when Venus was going to appear. So we had a kind of a world in those, probably, it's all in my imagination. I mean, I know what they did because we have some books about it. But I mean, when I say how it looked to them and how many, I don't know whether it was only the priests who knew how to calculate and all. I'm exaggerating a little bit. I tell the story as a model. Then there were these high priests who could predict Venus, and there were people who were the normal man, which we'll imagine said, God, I don't know how they do this. This is marvelous. It frightens me. I can't learn arithmetic. It's impossible, and so forth. Now, if there had been in those days an attempt at pedagogy, in other words, priests trying to explain to the layman what they were doing, they could explain that they were only counting. They were doing the equivalent of counting, okay? And then explain it. And the guys would say, but there's so much counting to do, it's so much work. Yes, and we made a more efficient way. But don't worry about the more efficient way. You're not going to do it. You only want to know what we're doing. We're just counting beans out of bowls. And we count beans, a certain number of beans, and then we can tell where Venus is going to be. There would be another reaction after you learn that. You'd say, but what is Venus? Why does it take 584 bowls? What are we doing? Was it a rock in the sky, which we think, or is it a goddess coming up, and why does she come up? What do the beans got to do with the Venus? Which is a nice question. Later on, we get this model of a ball in the sky going around with gravity and all this other stuff, but that's for another era. Now, it's very analogous here. I'm going to show you what all the rules of quantum mechanics are, and you're going to say, but why didn't we have to wait until you're a graduate student in school to learn that? It's the same as all they're learning is tricks to make calculations much more efficiently than the way I'm going to show you. I'm going to show you how to make these calculations as if you were taking beans out of pots, okay? It's as easy as that. It's something you'll be able to do. Drawing arrows on a piece of paper according to certain rules and seeing how long the final arrow is the rule I'm going to give you. I assure you that the kids in school who do this don't do it that way, just like the Mayan priests don't actually take the beans out of the bowl, but they're explaining what the effect is that they're trying to do, right? Although they do it with a much more efficient way. So with mathematics and calculus and hokey poke and this and that, there's a way of putting these arrows together that I'm going to explain, but I'm not going to explain that way because we don't have to for our purposes. All you have to see is what they actually do. Then your objection when you're all finished, you say, yeah, that's the way you make the arrows, but what is it that's going on? Which is the analog of, yes, this is the way you move the beans, but what has that got to do with Venus? And the priest says, well, I always predict when it comes, you see, so that's all I know about Venus. That's all I'm going to be able to do. That's it. So knowing that that's where we're going and explaining carefully what I want you to try to understand and what it is hopeless for you to understand, because almost hopeless unless you make a new brilliant discovery that no one else has yet made about how to understand these things. In other words, maybe one of the, and it's quite possible, one of the plebeians of Maya land, after the guy explained about the beans, would think a while and say, ha-ha, Venus must be a rock rolling around in the sky. Right? Maybe.
Or a big bean going around.
Or a big bean, yeah. So maybe you'll figure out it's a big arrow going around in the sky. But it's the same idea. Now, so then with that understanding of what I'm doing, I'm going to explain our rules for doing this. But I'm not going to explain the most efficient mathematical way of making those rules. I'm going to show you the number system and the calculus and all the other botch-watch, which is to do it more efficiently. But here's the way the rules go for this particular situation. And it'll look a little special for glass and so forth. It's a special circumstance. And I'll tell you as we go along more and more generally what the rules are. It's only Wednesday today, and it's possible that I can get to give you the complete system of rules for everything having to do with what we call quantum electrodynamics, but I'm not sure I can get there by Friday. I don't want to rush anything, so we'll just go as far as we can go. Here's the way this works. Here's the way we figure out what the chance is that something happens in a circumstance like this. Just let me tell you, it's crazy, but we're going to end up, all the calculations are done not by counting beans. As a matter of fact, they don't actually do that, but we make it. Not by counting beans, but by drawing arrows on a piece of paper, all right? The arrow has nothing to do with the picture, just like the bean has nothing to do, it's not a big bean in the sky, that's the wrong picture. The arrows have nothing to do with any of the directions in there. This piece of paper is another piece of paper. It's got nothing to do with the drawing I made over there. It's got nothing to do with the glass. No, it's just a calculation sheet. You go off to the right and start figuring, just like the beans. Nothing to do with Venus. What we do is on this piece of paper, we have a center. Maybe if you'd like to put a pair of axes, you might use cross-section paper if you want. That would be convenient. That's not important. We have an arrow. We calculate an arrow. That is, we make an arrow by some rules, how to make the arrow. That is, we have a pot with a number of beans with some rules about how many beans to put in. Well, we make arrows of a certain size. Then when we're done, we interpret the final arrow this way, that the square of the length measures the chance of an event. It goes like this. For every event that you want to ask a question for instance, in our case, the event is a photon leaves here and gets to here. We want to calculate the chance. Then there's a rule for finding a length of an arrow, finding an arrow for that case. And then after this arrow is found, the probability is proportional to the square of it. By the square means the length in whatever units multiplied by itself. Or what's equivalent, if you have that arrow, and you simply built the square on the arrow with all the same side, the area of that square is the probability. All right? Now I have to give you the rules for finding the arrows. And they work like this. When an event, if in this particular case, I'll give you some examples and we'll work out the rules all together, but I'm putting it together slowly. First, for reflection from one surface. The rule for the arrows works like this. that when you reflect from the surface, the front surface, you make an arrow 1/5 of a unit long in this direction. That corresponds to reflection from the surface. The length of it is 1/5 of a unit, 0.2, 1/5 of a unit. If there was only one surface, there's only that arrow, and that's finished. The area of the square, 1/5 by 1/5, is 1/25, or 4%, and that agrees with the experiment. All right. Now, if there are two surfaces, we must make two arrows.
Where'd you get that 1/5?
That's a property of glass. That's a special rule, okay, for glass. I'll come back to how those are calculated much later, when we talk about what glass is, made out of electrons, and how you figure that out. But at the present moment, I want to keep it elementary. I suppose that things have some properties. For glass, it's 1/5. If it were water, I think it's 1/7, approximately, okay? Different lengths for different substances. Let's say for glass, it's very close to 0.2, 1/5. Now, when we have another surface here, then the rule is for the second surface. For the second surface, it's also 1/5. Nice. Except it's in the opposite direction. It's the same as if it was a front surface, except that when it's the surface from air to glass, you draw the arrow one direction. When it's the surface from glass to air, you draw the arrow in the opposite direction. Right? So that's what you have to remember. Those looked very artificial, those 1/5. They come from the glass. We have to go later on. We'll get more complete rules by which more details can be worked out from the beginning instead of giving you something. But we're just these two. Now, you would think then, if that's right, no, but that's part of the rules. There's one more rule, two more rules. What happens when two things happen? It could either be the front surface or the back surface. Then what you do is well, let me just do it in an opposite order. The next thing is that if there's a certain distance that the light has to go for monochromatic light, actually that's equivalent to a certain time. I'd rather talk in terms of time. The distance to go from here to here is a certain time. The arrow must be turned depending on how long it goes. Okay? In other words, this 1/5 was what you would have got right here for the reflection. But if you want to know what it would be, that's if, in other words, the photomultiplier were right here. But if the photomultiplier is here, this arrow has to be changed for distance. So when it's changed for distance, this is not an arrow, this is a rule, a change. But how can I do this? A distance does this. The answer is rotate arrow. Actually, for the experiments that we're talking about, where the speed is always the same, the distance and the time might be the same. You could either way. And I might make a mistake, sometimes say distance and sometimes say time. They're always proportional for our experiments, almost for our experiments here. It's really time that counts. So let's leave it correctly. It's time. You rotate the arrow at a certain rate, a certain number of rotations for every second. Okay? You rotate the arrow around. So, for example, if the time is short, very short, this arrow, if the photomultiplier is not exactly at this surface, but just back a little bit, then the arrow would be slightly tilted. If the photomultiplier were further back, still it would be tilted more. Angle would be increased. In fact, the angle is simply proportional to how far it is away. It's like a clock, in fact. You could imagine it as the hand of a clock, which is, except I've made it go backwards, right? I mean, clocks usually go the other way. It's the hand of a clock, which is measuring how long it is to get to here. And it goes around as it gets to here, all right? Actually, for any reasonable distances, this is a very large number of turns. It turns once every, for yellow light, something like 25, well, we talked about it before, 40 millionths of an inch, but that's an even shorter time. How long does it take light to go 41 millionths of an inch, going at 186,000 miles a second? That's the amount of time it takes to turn that once, okay? Each time, for each 40 millionth of an inch of light time, this thing is turning once, so it's going around pretty...
One wavelength?
Yes, that's exactly what it... Precisely.
Sodium lights are about 5,000 amps.
Yes, yes. which I was saying is 41 millionths of an inch, I think, if I haven't made a mistake in arithmetic.
500 nanometers.
But the time is very short to go that distance, and that's the time I'm talking about, okay? Now, we have, of course, let's suppose that the first arrow, as a result of having a photomultiplier 16 miles away, or 16 centimeters, that this is turned billion times and a half around and it ends up here, okay? Now what would happen to this arrow? I'm sorry, I made an error. I should be the total time from when it left here to here to here, okay? So excuse me, it's the total time that turns, how much you have to turn it. Now this time, when I go from here to the back surface in here, I also have to turn it by the total time. So this arrow has to also be turned by a very large time. But they're not equal. They're not equal because the total time to come down to here and come back to there would be longer than to go from here to here. So this one is turned more than the other, if there's any thickness in here. So let's say it's very thin, then it's only turned a little bit more. Let me take the case that it's turned just a little bit more. Then this arrow, if it were turned exactly the same amount as this has gone rotated 6 billion times and a half. This would be rotated 6 billion times and a half and would come out there. That's the way it would look if the times were exactly equal, right? Because they were opposite to start with, and if they both keep turning the same amount, they'd always stay opposite. However, this turns a little bit further depending on the thickness, and therefore, in fact, this is not really what it is. It's more like that. Okay? All right. So far, we haven't computed anything, just found the arrow with 2 arrows. Now, the situation, the rules go, I'm just developing them in this example, and we'll develop them as we go along. The special rule about the 1/5 was special for glass. The speed of turning is special for the color. A different color turns more rapidly per second. But the more important and general rule that I'm about to mention is how you put together something can happen in more than one way. We have a situation in here in which we say, when we get the light here, we could say, it's either reflected from the front surface or the back surface. I taught you not to say things like that. If you're not observed it, don't say either. Either in the sense of calculating arrows. It's a situation in which there's a way that you could think of it as happening, and there's another way that you can think of it as happening. For each one, we have an arrow. We now have